Hello! In the last video, we learned how to call the setPhenotype function and delegate the implementation of the Genotype-Phenotype map to separate Genotype-Phenotype map classes for each of the phenotypes we are interested in evolving. In this video, we'll stick with the operation where we specify the Genotype-Phenotype maps. We will go over how exactly you can set up the Genotype-Phenotype map to effectively leverage GPU parallelization using SPEGG. Indeed, at this point, the code is going to start to use thrust parallelization capacity. If you're simulating a very large number of individuals, you can imagine how long it could take you to calculate a lot of genotype-phenotype maps. So what the SPEGG framework aims to do is leverage GPU parallelization. To do that, we're going to use something called functors. For our purposes, you can think of functors as functions that can be performed parallel across several individuals in your simulation. In CUDA thrust, functors are represented using structures, a type of variable from C that is superficially reminiscent of classes from C++. Functors are coded in a very specific way, but the basic formula is generally the same. For more details about them, we refer you to the documentation for the thrust library itself. We will illustrate the use of functors by taking a specific example here. We'll define our first functor to be a function that actually calculates the genotype-phenotype map for fecundity. That is, given input about the individual's genotype, it returns that individual's corresponding phenotype. Let's call this functor fecundity calculator. Here's how we'll define our functors. First, you define the name for your functor and declare it as a structure. In SPEGG, our functors operate on a specific kind of input. The first kind of input are entities called thrust tuples. What thrust tuples do is they essentially bind together several different vectors for efficient calculation on the GPU using functors. The key task of your functor is therefore to define an operation that performs calculations on these tuples. The second type of input involves pointers to vectors, but we will defer a discussion of them to the next video. The way a functor that operates on tuples is implemented in thrust is as follows. We declare an operator that returns a void and reference an arbitrary tuple which we'll call t. If we would like our functor to evaluate its function on the GPU, we have to specify that by typing device. We can also allow it to run on the CPU and thus type host. The functor itself isn't aware of what a tuple is, so we'll call a template and specify the type name as tuple. Now we can define the behavior of a function inside the braces, but I'm going to hold off on that for now. First, we'll want to specify what each index of a tuple refers to. Remember, a tuple binds together several thrust vectors. Thus, the ith index of the tuple refers to the ith vector that is used to make our tuple. And a functor does operations on the values of those vectors for the jth individual in parallel on your graphics card. Now we can define a genotype-phenotype map that looks something like this. The phenotypic value we want to calculate for each individual is defined as the sum of midpoints of their maternally inherited allelic value and their paternally inherited allelic value at the locus with index 1 and locus with index 2. Let me illustrate this idea a bit further in this code segment. In a serial context, we might write code that looks something like this. This will iterate over all individuals and determine their phenotypes based on their genetic values at two loci, where the F genotype and M genotype refer to genotypes inherited from the female and male parent, respectively. The phenotypes will be stored in the vector phenotype index. The first variable in square brackets represents the index of the locus comprising the genetic architecture of the phenotype. The second variable in square brackets refers to the index of the ith individual. Each of these 5 vectors will then be zipped together to create a tuple. And therefore, that tuple will come to look like something like this. So now we want to define our operator to perform operations on each of these tuples. To access the first vector involved in a tuple, in thrust you can do this by typing thrust get 0 t, which always corresponds to the vector describing the maternally inherited allelic value at locus 1. And so we can define our genotype-phenotype map as and that defines our functor. Now remember how we defined a member function of our genotype-phenotype map class called calculate-phenotype? Well, now we will specify what this function does, and it will be responsible for actually invoking the functor. So let's go back to our .cu file. We'll make a function called calculate-phenotype that is a member of our fecundity-phenotype class. Now, recall that for code running on a single CPU, we had to use a for loop to iterate through each individual sequentially. But we are going to parallelize our fecundity functor across individuals in our model. Thrust automatically takes care of this using a function called thrust for each. Thrust for each takes 3 arguments. First, a pointer to the first element of your tuple. Second, a pointer to the last element of your tuple. And finally, the functor on which you want to perform your calculation. But we need to convert our vectors into tuples. To do this, we'll call the thrust function thrust_make_tuple. Now we'll populate this make tuple with pointers to the first elements of the vectors involved. Recall that here, we perform the genotype-phenotype map operation on individual from index case through num kids. Finally, we wrap this tuple once more using thrust make zip iterator. We'll repeat this process with pointers to the last element of the vectors involved that we want to calculate. In this case, index case plus num kids. Now we'll tell for each to run the fecundity calculator functor on these newly created tuples. This code is now set up to run on the GPU, and each element of the tuple will be executed in parallel on the GPU's many cores. In the next video, I'm going to go through how you can define a slightly more elaborate functor that takes arguments other than the vectors of tuples. Thank you again for watching, and if you have any questions, shoot me an email via our mailing list, speg-users@googlegroups.com.